So what we have here is a simple acids and base problem. So looking at the dissociation constants of HOCl and HOBr, you can see that the dissociation constant for HOCl is a little bit bigger because it's times 10 to the negative 8th up here, and 2.9 times 10 to the negative 8th is in fact bigger than 2.4 times 10 to the negative 9th. So with that in hand, you can justify your answer by saying HOCl is the stronger acid, as its dissociation constant is much greater than that of HOBr. So what that means is that HOCl will dissociate more and that it is stronger acid. And that is your justification.
Okay, so in this part of the question, we are going to draw a complete Lewis electron dot diagram for the acid that we identified in part A. And the acid we identified was HOCl, okay? And so, first things first, we want to see how many valence electrons each one of these atoms has, okay? So we look at chlorine, and it has 7 valence electrons, so we're just going to put a 7 right under here. And oxygen has 6 valence electrons, so we're just going to put a 6 right here. And hydrogen has 1 valence electron. Okay, and so when we're drawing our Lewis electron dot diagram, we want to make sure that each dot represents electron and it adds up to 14, because 1 plus 6 plus 7 equals 14. Okay, so we're just going to draw out HOCl. Okay, we're going to bond each atom with a pair of electrons. And we're going to fill in little dots of electrons everywhere that there currently aren't any. Okay, so that's basically it, and to check our work we can count each one of the dots and hopefully it'll add up to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that is your answer.
So moving on to A3, we have the question that is hypoiodous acid has formula HOI. Predict whether HOI is stronger acid or whether it is weaker than HOCl. So we have the diagrams drawn out here. And looking at our periodic table, we can see that iodine is lower in the halogen group than chlorine is. And so we know that the general trend of electronegativity is that as we go down the group, the electronegativity decreases because we're going farther away from fluorine. So we can see that in these diagrams that the electrons here will be more attracted to chlorine than the electrons of the oxygen over here. So we see that the bonds between the chlorine and the electrons are stronger, meaning that it has a hard time breaking them apart and dissociating into an acid. So the same principle can be applied over to HOI, in that the electrons are less attracted to the iodine, meaning that it's an easier time splitting them apart and thus becoming an acid, meaning that hypoiodous acid is in fact weaker than HOCl.
Okay, so for part B, what we're going to do is we're going to write the equation for the reaction that occurs between hypochlorous acid and water. Okay, so what we're going to do is we're going to write hypochlorous acid, which is HOCl, and we're going to get a little bit of H2O, and then so that gives our conjugate base of HOCl, which is OCl minus, and since HOCl is a proton donator, it's going to lose its hydrogen and it's going to give it to the H2O, which is a proton acceptor. Okay, so and we get to write H3O plus. Okay? And since the reason why it's a plus is because it's gaining a positively charged H ion, and the reason why OCl is minus is because it is losing a H atom. So we can write this, or we can get rid of H2O and the H3O, and we can write HOCl gives OCl minus plus H plus. And both are acceptable answers.
Moving on to the next part, we have the question asking, write the equilibrium constant expression for the hydrolysis reaction that occurs between OCl minus and H2O. So we have our equation written out here, OCl minus plus H2O, giving hydroxide plus hypochlorous acid. And so we see that the water acts as the proton donor in this case, giving the hydrogen to the OCl minus to form HOCl, and in the process it loses that hydrogen and becomes hydroxide. So we know that the equilibrium constant expression is equal to products over reactants, excluding water, and that would be equal to our products, which are OH minus and HOCl, over the reactants, excluding water once again, which is OCl minus. Now, if you had coefficients for these, say you balanced it in a way that this was 2 or this is 1, you would need to put the 2, the coefficient, into the exponent of the whatever reactant or product you are talking about.
Okay, so in part C2, we are going to calculate the value of the equilibrium constant at 298 Kelvin for the hydrolysis reaction. What we're going to do real quick is we're going to draw the hydrolysis reaction, which is OCl minus plus H2O, and it gives HOCl plus hydroxide. Okay, now since it gives hydroxide, our equilibrium constant is going to be Kb. Okay, so B for base. Okay, and so we can say that Kb is equal to the Kw divided by the Ka. Okay, and so the Kw is a constant, which equals 1.0 times 10 to the negative 14. Okay, and so since we're given in the first question that the Ka for HOCl is 2.9 times 10 to the negative 8. So we're just going to divide these two, and we'll get Kb for the hydrolysis reaction equals 3.4 times 10 to the negative 7.
So moving forward, we have a simple ice problem here. It asks to calculate the value of the OH minus hydroxide concentration in the 1.2 molar solution of NaOCl at standard temperature, which is 298 Kelvin. So if we use the Kb value, which we calculated in the last problem, which turned out to be 3.4 times 10 to the negative 7th. Alright, so let me put that somewhere over here so it's not in the way. Just put it, how about over here? Kb equals 3.4 times 10 to the negative 7th. So, we have a simple ice problem. We ignore water as in all ice problems, and the value of OCl minus is 1.2 molar initially. The change is minus x, 1.2 minus x at equilibrium. So we have 0 concentration here, and 0 concentration here initially. The change is plus X for both OH- and HOCl. And at equilibrium, it's just going to be X and X. So, what we have here, we set all of these equal products over reactants, our Kb value. So 3.4 times 10 to the negative 7th is equal to X times X, which is X squared, over 1.2, and minus X. And using the 5% rule, we can ignore the minus X, so it just becomes 1.2. We multiply 3.4 times 10 to the negative 7th by 1.2, and we end up with X squared, which equals to, okay, so I have my calculator now, and what we do is 3.4 times 10 to the negative 7th. We multiply that by 1.2, and that gives us a value for X squared is equal to 4.08 times 10 to the negative 7th. And because we're looking for X, we square root this value, and we find out that X is equal to 6.38 times 10 to the negative 4th. And that is the concentration of hydroxide in the 1.2 molar solution at equilibrium.
Okay, so in part D1, we need to calculate the total value of H3O plus in the buffer solution. Okay, and so we are given that pH equals 6.48, and to find the concentration of H3O, we can simply just do the concentration of H3O equals 10 to the negative pH. Okay, and so since we know the pH, all we have to do is just plug in 6.48 into this equation, and so we get H3O equals 10 to the negative 6.48. Okay, and so that equals 3.3 times 10 to the negative 7 molar. Okay, so the H3O plus concentration is 3.3 times 10 to the negative 7.
So moving on to the last part of the question number 1, we're asked to find which of the following, HOCl or OCl minus, is present in the larger concentration of the buffer solution. So we know that Ka is equal to products over reactants, which is equal to H plus times OCl minus over our reactants, which is HOCl. We know the Ka value, which is 2.9 times 10 to the negative 8th. And that is equal to, we know the value of the H plus, which we just calculated, as 3.3 times 10 to the negative 7th, times the OCl minus concentration over the HOCl concentration. And so, with that, we can calculate that the OCl minus concentration over the HOCl minus concentration, or the HOCl, excuse me, is equal to 2.9 times 10 to the negative 8th or divided by 3.3 times 10 to the negative 7th, which gives us a value of 0.088. And because this is not greater than 1, this number is less than 1, that means that the HOCl concentration must be greater than the OCl minus concentration.